Welcome to Maths with EJD. In this video, I'm talking about differentiation and integration of power series. Differentiation and integration of power series. Okay, that's what this is about. And if you have not subscribed to this channel, be sure to do that and make sure you hit the notification bell so you can always get alerted when a new video is released. And don't forget to comment, like, and share so that more and more people can get benefits from this channel. Okay, so definition and integration of power series. Let's start with differentiation. Differentiation of power series. So, cause given a power series of the form f of x equals summation from n equals 0 to infinity of usually an into x minus c raised to power n. So you differentiate term by term. So here we differentiate term by term. So, and what that simply means is this, that if this is f of x, then f prime of x is something like this. It's summation. Now, because, most likely the first term is going to be like a constant or zero or something like that. So, when you differentiate, it shifts from n equals 0 to n equals 1, and then it goes up to infinity. And then, of course, you have the an, which is the coefficient, usually like that. And then you do it, you now behave like you're differentiating function of a function, just like we saw in the last video, where you bring down power n, so you have an times n times x minus c, the center, raised to power n minus 1. So that's what the derivative of that would look like. Okay. So let's see some examples. Let's say we have example one, where we consider the function, f of x equals summation from n equals 0 to infinity of x raised to power n. So to differentiate, we have f prime of x, which is now equal to summation. Now, n equals 0 becomes n equals 1 when you differentiate, and that goes to infinity. Then, of course, there's no constant in this case. So bring down the power n. So you just do it like you're differentiating a normal function. So you have n, then x raised to power n minus 1. And that's what you get. So that's the derivative of that. So you see that, of course, you may want to expand this to see what it looks like. So it's like, so you have summation from n equals 1 to infinity of nx n raised power minus nx raised power n minus 1. So at n equals 1, it means you have x raised power 0. At n equals 2, you have 2x raised to power 1. At n equals 3, you have 3x raised to power 2, at x equals 4, you have 4x raised to power 3, and so on and so forth. So you see a pattern there already. So this is like 1 plus 2x plus 3x squared plus 4x cubed plus 4x cubed, and so on and so forth. Okay. Yeah, so you can see here, this is actually looking like it's a geometric series. So we can say this is a geometric series. This is a geometric series where the derivative is f prime of x, which is equal to 1 over 1 minus x all squared. Okay, so of course, I mean, I've done something close to this in the past. So this is actually a geometric series, right? With the first term a, and the common ratio, it has a common ratio. So this is like multiplied by 2. Is it multiplied by 2x? That's like 2x over 1. That's 2x. Okay. I mean, this not working. Okay. I'm not sure this is gonna work because there's no common ratio. 3x squared over 2x is 3 over 2x. So it's not a common ratio like that. Okay. So let's just stop at that. That this is a geometric ratio where the derivative is f prime of x equals 1 over x, 1 over 1 minus x all squared. And condition is absolute value of x is less than 1, like that. So that's an example right there. And then we go to the next one, example 2. Example 2. Example 2, consider the Maclaurin series for sine x. Okay, the Maclaurin series for sine x is actually this. You have sine x equals, okay, this is like the formula for it. We know sine x is odd, so we'll be having x minus x cubed over 3 factorial plus x raised to 5 over 5 factorial minus x raised to 7 over 7 factorial and so on and so forth. But the formula is this because it's an alternating series, so we have minus 1 raised to power n. So this minus 1 raised to power n is what makes it alternating. So when n is even, that you have positive. When n is odd, you have it negative. So and then this is x raised to power 2n plus 1 all over 2n plus 1 factorial. So this is like a generalized formula for that. So if you substitute the values, okay, for instance, if you put 0 now, this is 1, this is x raised to power 1 plus 1, this is 1 factorial. So it's actually that x as usual that you have, and then you put 1, so you have minus, so that becomes negative. Minus 1 raised to power 1, that's negative, and then this is x raised to power 3 over 3 factorial, like you already have. So but having it this way makes it easy to differentiate. So if you differentiate term by term, differentiate this term by term. So that gives us differentiate sine x, you get cos x, right? And because you get cos x, that will be equal to summation. Oh, okay, cos x itself, like we said, right, is d dx of sine x. When you differentiate sine x, you get cos x. And that is equal to summation from n equals 0 to infinity. So here, because it's you end up going back to the start, right? So here we have see what happens. We have minus 1 raised to power n because that one is a coefficient, and that's not what we are differentiating. So the next thing is we have x raised to power 2n plus 1. That's where the differentiation takes place. So you bring down the power, that's 2n plus 1 coming down times x raised to power 2n plus 1 minus 1. That's simply 2n up there. And then down here, you just have 2n plus 1 factorial. So the main action is happening with this one, with x raised to power 2n plus 1. So you can just tidy this up now to get the full picture. So you have summation from n equals 0 to infinity, and then you have minus 1 raised to power n, okay, multiplied by 2n plus 1, multiplied by 2n plus 1, times x raised to power 2n all over 2n plus 1 factorial. So that's what you have. But then I can see something to work on here. This is 2n plus 1, then you have 2n plus 1 down there. So, and that's why, I mean, the whole thing goes back to 0 again, because cos x also has its own formula before, which aligns with what you end up getting from here. So if we try to tidy that up, it means we have summation from n equals 0 to infinity of minus 1 raised to power n. Then this is 2n plus 1, x raised to power 2n all over. So 2n plus 1 factorial is the same thing as 2n plus 1 times 2n plus 1 minus 1. That's 2n. So that'll be 2n factorial like this. So this cancels this. And then we see that cos x, we see that d dx of sine x. That's the derivative of sine x, which is actually the same as cos x. It's simply summation from n equals 0 to infinity for minus 1 raised power n, then x raised power 2n, all over 2n factorial. So now this becomes an even function, because if you put 0, if you put 0, you get 1 there, and you have x, you also have 1 all over 2n factorial. That's also 0 factorial. So everything there is 1. Then if you put 1 itself, okay, I think this we need some clarification on this. Let me see what happens with that. Okay, d dx is equal to that. So if we have, okay, of course it alternates too, right? So if you put 1, you have minus, if you put 1, you have minus, so that's going to be negative x raised to power 2 over 2 factorial, and that aligns with what we've already known with cos x. So so this also proves that if you differentiate sine x, you get cos x settled. Okay, so so this is actually the series for cos x, as we already know, so no worries. And then we go to example 3, the third example under differentiation. Example 3. So consider the exponential function, the exponential function e raised power x, whose series is e raised power x equals summation from n equals 0 to infinity for x raised power n all over n factorial. Okay, so the derivative, that's also the differentiation. The derivative is f prime of x, and that is summation from n equals 1 to infinity. So here again, so you can see there's shifting again, but for sine and cos, there's no shifting like we saw the other time. So you have n equals 1, right? And then this is differentiate normally. You have n x raised by n minus 1 all over n factorial. Okay, so if that is the case, we can now see what's going to happen here. So we have summation from, so we are going to, so it looks like we want to take it back to where we are coming from. So if you want to shift alongside with this now, so it means we have to go back to 0. So see what is going to happen. So you have n times x. So you're taking it a step back. Okay, let's even do it this way, so the picture can be clear. So n equals 1. I'm trying to see what we can do there. Okay, so this is nx raised to n minus 1. So if we have to go a step backwards, right? So it means we can simply have n equals 0. N equals a summation from n equals 0 to infinity, and then that clears off this n. So that takes away, that automatically clears off the n, and then we go back, then it clears off the n, and it takes it one step backwards. So instead of n minus 1, we still come back to x raised power n of n factorial, and then it's like we're back at where we started from before, and this is still the same thing as e raised power x. So going back from n equals 1 to n equals 0 takes away this n, and then knocks off. Okay, I think a better explanation, this would be a better explanation. Let me do it this way. Okay, so see what is happening here. So we have this, right? And then this is summation from n equals 1 to infinity, and this is nx raised by n minus 1 all over n factorial is actually n times n minus 1 factorial. Okay, so n cancels n, so we have still summation from n equals 1 to infinity x raised by n minus 1 all over n minus 1 factorial. So this is us starting from 1. Okay. But if we shift it to the back, and so it means if we add one term to each part. So if we add one term to each part, so that means if you add one term to all this, then it means you are subtracting 1 from this part. So that's summation from n equals 0 to infinity. And that takes it back to where we are coming from, n factorial. Okay. So because we're at 1, we're moving one step backwards. So so that means you're adding one term to this part now. So, and this is simply the same thing as where we started from n equals 0 to infinity. And this is e raised power x. So, and that is always the truth that this shows, right? This confirms, as we have always known, this shows that the derivative of e raised power x is itself, like we've always known. So when you differentiate e raised power x, you get e raised power x. Oh, sorry, I think this is a mistake. This is just e raised power x, no summation anymore. So the whole expression is e raised power x. If you remember, that's where we started from. E raised power x is summation x, from n equals 0 to infinity of x raised power n over n factorial. I think the tricky part is this part now, where, having it this way. So since you're starting from n equals 1, having differentiated. So if you want to go back to 0, so it means you're adding one more step to this. So you have x raised power n over n factorial. So this shows that the derivative of e raised power x is itself. So that's that about differentiation of power series. So let's move on to integration of power series. Integration of power series. So talking about the integration of power series, right? Let's see this, that given a power series, f of x equals summation from n equals 0 to infinity of an into x minus c raised power n. This is a typical power series you've always known. So you need to know that the integral is integral of f of x dx, which is so the integral of f of x dx now is you integrating. It's basically you integrating all this with respect to x. So that's like you have now integral, of the summation from n equals 0 to infinity an x minus c raised power n dx. Okay. And once that happens, see what's going to happen. You have summation from n equals 0 to infinity of the normal an that is there now. Then this power n, normally when you integrate, right? When you integrate x raised power n, if you integrate x raised power n with respect to x, that means you have x raised power n plus 1 all over n plus 1. So increase the power of x and divide by the new power. Basically, that's the idea of integration. So an is constant, that's because it's a coefficient. Then the power of n is actually up there. So you have x minus c raised power n plus 1 divided by n plus 1. Okay. And that's plus an arbitrary constant. So it's more like the normal differentiation thing you do. So, and this is equal to summation from n equals 0 to infinity, from n equals 0 to infinity. And then you have an all over n plus 1 as a constant, now the new coefficient, then x minus c raised power n plus 1. Of course, plus an arbitrary constant because this is c, right? I can say this is an arbitrary constant k. Let's call that k. Okay, let's make that k to avoid confusion. Okay, so that's what we have generally for integration. Okay, this is times, this is multiplication in case it looks confusing. Sometimes I just use dot for multiplication. So be sure that you understand that. Okay, let's look at some examples. So we can say this is example from everything we've been doing, right? Okay, let me just say example 1. Let me restart it. example 1 for integration, right? That will be this. Consider f of x. That's e raised power x that we just finished. Oh, okay, not exactly. Consider f of x equals summation from n equals 0 to infinity of x raised power n. So if you have this, right? So if you integrate that, that is integral of f of x dx, and that is integral of summation from n equals 0 to infinity of x raised power n with respect to x. Okay, so that's simple. Just having, of course, if you integrate that, you still have summation from n equals 0 to infinity of, so x raised power n plus 1, that's a new power, divided by that new power, and then add an arbitrary constant k to it. And that's all you have. So you can see that the integrated series, the integrated series is integral. Okay, in fact, normally, right, this integral, okay, let me make that statement. So this is like geometric series, right? Let me just do a bit of expansion. So that's integral of when n is 0, right? You have x raised by 0, that's 1. When x is 1, you have x. When x is 2, you have x squared, and so on and so forth. Dx. Okay, so that's like the usual, geometric series we know, and that is why this is more like you're integrating 1 over 1 minus x dx. I've done this a couple of times, talking about sum to infinity. So, and that's why we are bringing that up here, that the integrated series is actually the same as saying dx over 1 minus x dx. And then, of course, if you differentiate 1 minus x, you get minus 1, which you have at the top. So, I mean, this is as good as 1 over 1 minus x dx. So, if we say, so if you differentiate 1 minus x, the dx of 1 minus x is equal to minus 1. So 1 is not exactly, 1 is not the same thing as minus 1, but we can actually take care of that by saying now that if we want to integrate that, we have integral of dx over 1 minus x dx, and that is equal to, so now if you can multiply the top by 1, so you have integral of minus 1 times minus 1 times, this is the one that was there, this one that was there before, all over 1 minus x dx. Now, we have not done anything wrong because minus 1 times minus 1 is 1, okay? So if you multiply something by 1, nothing has changed. So, but what we want to do is we want to make sure that the top here is minus 1. So we can bring this minus can come outside. So we have minus integral. Then this minus 1 times 1 is minus 1, all over 1 minus x dx. So if you check the integration playlist, you'll understand what I'm trying to do better. So this is now, so now if you differentiate 1 minus x, you get minus 1 at the top. And the rule for that is whenever that happens, then you can just say the answer is the natural logarithm of 1 minus x down here. So that's why you now have this minus outside times ln of 1 minus x plus c. Okay? And then and that happens for absolute value of x less than 1. Okay? So that's the idea right there. So all of these things can come together. So if you are confused about what I've just done here, you can check out the basic calculus playlist and check under integration of integration by I think, yeah, the second type of integration, right? That's the derivative function ratio, something like that. Okay, so that's that. Then we take another example. That's example 2 under integration now. Example 2 under integration. So now example 2 under integration. So we consider the Maclaurin series. Consider the Maclaurin series for cos x. Okay, that is cos x equals summation from n equals 0 to infinity of minus 1 raised to power n, x raised to power 2n. This is the result we got when we differentiated sine. So now I want to differentiate it and see what we get. Normally, we know when we differentiate cos, we get minus sine. So let's see if that is true, even from the point of view of power series. So we have to integrate. So we integrate. Of course, we know integral of cos x, integral of cos x dx should actually be something like minus. No. When you differentiate sine, you get cos. So when you integrate cos, you should get sine back. Yes, that's the idea. So we integrate integral of cos x dx is actually sine x, as we know already. So it's actually sine x. So, and let's see how that happens here. That means we have integral of summation from n equals 0 to infinity of minus 1 raised to power n x raised to power 2n divided by 2n factorial. So we haven't done anything. So this is just us writing it out, dx, right? So now to integrate, the focus is on the power of x. So we have summation from n equals 0 to infinity, and you have minus 1 raised to power n. Now, and you can also bring 2n factorial down here to avoid confusion there. So this multiplied by x. So for this x now, you increase the power by 1. That's 2n plus 1 divided by the new power 2n plus 1. Then, of course, you have to add an arbitrary constant, c, or I've been adding k. So let's call it k in this case. So, that's what you have, right? And you can tidy that up if you like. You can tidy this up because now you see this is summation from n equals 0 to infinity. Then you have minus 1 x minus 1 raised to power n, x raised to power 2n plus 1 all over. So you see 2n plus 1 multiplied by 2n factorial. So it's more like you're saying 4 times 3 factorial. That's simply 4 factorial because 4 factorial is 4 times 3. Okay, maybe I should do it in a more intuitive way, so to speak. So 4 times 3 factorial, that's like 4 times 3 factorial. So that's like 4 times 3 factorial is 3 times 2 times 1. So, and this is simply 4 factorial at the end of the day. Okay, so it's simply 4 factorial at the end of the day. So it means that this is simply summation from n equals 0 to infinity of minus 1 raised to power n, x raised to power 2n plus 1 divided by 2n plus 1 times 2n factorial. That's simply 2n plus 1 factorial. And if you look at this, it's the same sine x we had the other time, because of course we know when you differentiate cos x, when you integrate differentiate sine x, you get cos x. So integrate cos x, you get your sine x back. So this is simply, of course, don't forget the arbitrary constant. So this is simply sine x that we've already known before. Okay, so you see that the result is the series, for sine x, where c is equal to 0. So, where k is 0, if you set k to 0, that's arbitrary constant to 0. So you get sine x. So, and that is for the Maclaurin series, Okay. So that goes, and we take the last example under integration. The last example 3 under integration. So example 3. So for the exponential function, which is e raised to power x, so we have integral of e raised to power x dx. That's simply integral of summation from n equals 0 to infinity of x raised to power n all over n factorial plus an arbitrary constant k or c or whatever you choose. So in this case, we just have so you can rewrite it as integral from summation n equals 0 to infinity of 1 over n factorial. We keep that aside so we can have only xn here plus k. So we can now have integral. So if you integrate that now, you have 1 over n factorial times x raised to power n plus 1, increase the power of n by 1, the power of x by 1, divided by the new power n plus 1, and then of course plus k here. And then you see like what I just did. This is x raised to power n plus 1 all over n plus 1 multiplied by n factorial, okay? Plus that constant k, right? And then you have x raised to power n plus 1, all right? All over n plus 1 factorial plus c. So, and with this, we are back with the exponential function. So we are back with the exponential function. So this will simplifies. Sorry, I forgot something. Oh, okay, this is n factorial. So n plus 1 multiplies that. So we have n plus 1 factorial. Yeah. So this simplifies. So that's now summation from n equals 0 to this. Okay. So this simplifies to e raised to power x plus the arbitrary constant k or c as expected. So there we have it. Yeah, so what else can I talk about here? Yeah, there are some key points to take note of. Thank God I remember this. So some key points to pay attention to when we do differentiation and integration of power series. So key points. The first point is that differentiation, like we know, differentiation reduces the exponent. It reduces the exponent by one and multiplies by the previous exponent So that's like when you bring the power down and the original power reduces by 1. That's what this is talking about. Multiplies by the previous exponent. Okay, that's the first point. The second point is that integration increases, like we know. So increase the power by 1 and divide by the new power. Integration increases the exponent, by 1 and divides the new exponent adding a constant of integration. That's the arbitrary constant, a constant of integration. So if you are coming across the idea of arbitrary constant for the first time or constant of integration, you want to check the basic calculus playlist still under integration. That is clearly explained why we always have that when we integrate. So then this is about the most important points, which may be new to some people, right? So the series after differentiation, differentiation or integration maintains the same radius of convergence, So after you differentiate or integrate, the radius of convergence of the series doesn't change. It remains the same. Okay? So with this, we come to the end of differentiation and integration of power series. If you have not subscribed, be sure to subscribe, hit the notification bell also so you can always get alerted when a new video is released. And of course, you want to comment, like, and share so that more and more people can benefit from this. Bye.